Go ahead and get started here. So thanks all for coming and listening to our talk here. Thanks for Nullcon for having us here. We're really excited to be presenting here. Our talk is titled Careful Who You Trust, Compromising P2P Cameras at Scale. And we got a lot of material to pack into the next 25 minutes, so we're going to do our best to get through it. Might be a few minutes over. We're only going to spend a few seconds here introducing ourselves. So my name is Jake Valletta. I'm a director based in San Francisco. Our artwork here, we're all based in San Francisco. And we all work at Mandiant for the record here. I've been around for 10 plus years in offensive security. I like mobile security, embedded, and also some reverse engineering. And these are all kind of the aspects that went into this research. I'm going to pass it over to Eric here.
Hey, I'm Eric Barzdukas. I'm a manager on our practice services team, focusing specifically on like mobile applications, embedded devices, running Frida wherever I can, successfully or otherwise.
Hey everyone, I'm Franke. I did my undergrad and master's at Stanford University in security, and focuses and interests are AppSec, static code analysis, and reverse engineering. So we're gonna jump right into things. Our agenda today is gonna first be talking about some embedded device security research we did on P2P cameras, and then moving on to looking at the P2P network that actually connects those devices together. Then we're going to discuss a critical security vulnerability we discovered in the peer-to-peer network, and then move into a series of case studies of devices we were able to fully compromise completely remotely. Then we're going to talk about conclusions and some next steps. So our initial research started actually in the fall of 2020, and it was motivated by nothing other than just a sheer interest in embedded device security and wanting to learn more. We really didn't have any specific objectives in mind here. We just bought about 12 P2P IoT cameras and started hacking away. Some common themes that we saw on all these devices are, we would start with some embedded testing, look for JTAG UART inputs, get a shell on the system, and then move into looking at mobile applications that were used to communicate with the devices, then move into reverse engineering binaries on the actual cameras and the mobile applications themselves, and then finally looking at web APIs that the mobile applications used to talk to those P2P cameras. So within the first day on most of the devices we looked at, we had rooted them. There was essentially no security involved in, as you could imagine, most IoT devices. But what really caught our eye as we started looking at Wireshark was really zero TCP traffic, but a ton of UDP traffic of just complete binary looking data with not high entropy and some interesting patterns we saw. So after looking at this further, we realized that this UDP traffic was actually the Calais protocol. The Calais network, peer-to-peer network, is developed by a company called ThruTech out of Taiwan. It is a platform for connecting at scale IoT devices. And it allows you to remotely connect all these devices and allow them to talk to each other and allow clients to talk to them through mobile applications or other clients. So they boast having over 83 million registered devices on their platform and 1.1 billion monthly connections. These devices range from security cameras at home to pet cameras to baby cameras. You really have kind of the whole 9 yards here. So the Calais platform is implemented as an SDK that you install on the IoT camera, and then each device gets assigned a specific UID, and then this UID is used to communicate. There's 4 main layers. The first layer consists of device discovery and connectivity, so actually routing traffic from a mobile app, for example, to your smart camera. Then there's the authentication layer. There's an audio-video streaming layer. And then there's a remote procedure call layer called IO control, which exposes some interesting functionality on devices. So we spent about 6 months of intensive research looking at this protocol, reverse engineering it, looking at the binaries on cameras, and we developed over time a comprehensive Python library to actually act as a client on the Calais platform. So we could send and receive messages through this UDP protocol, and act as if we were a device on the network. And through this, it led to the discovery of CVC 2021-28372, which is a device impersonation vulnerability that allows an attacker who knows the UID of a device on the Kali platform to compromise that device. So this means an attacker could compromise up to 83 million IoT cameras on this platform. Unfortunately, we don't have time to go too into the technical details here, but you can talk to us afterwards or read a blog that we published on August 17th with the US Cybersecurity Infrastructure Security Agency. ThruTech, we should note, shared recommendations for this on their website to update the ThruTech library version on the cameras, as well as use their off-key and DTLS features. So we'll quickly walk into what this vulnerability looks like. I should first note that the mobile application you see here, the attacker device, and the smart camera are all on completely different networks. As an attacker, we are going to, using our Python library that we wrote, spoof a request to register a victim's camera whose UID we know on the Kali network. The Kali network will then register that UID on the platform, but it will think that the UID we registered goes back to the attacker. So then when a user requests to view, for example, camera footage on that device, they'll connect to through their mobile app, initiate a Kali connection, except that connection will then be routed to the attacker. So the attacker will then receive device credentials for that IoT device. So the real question is, what's next here? This vulnerability that we disclosed allows an attacker to obtain credentials needed to talk to remote devices anywhere, regardless of NAT, firewall setup. This protocol punches through all that. So very, very bad. It also allows for immediate implicit compromise of audio-video data, which definitely scares a lot of people. And it also allows the unauthorized use of the IO control layer, which I mentioned. Now, this is where we really got excited, looking at functionality exposed by this. And we're going to talk in the rest of this talk about, the implications of this. What if we actually found bugs in the IO control layer that allowed us to exploit specific vulnerabilities within IoT cameras themselves? And for that, I'm going to pass things over to my colleague, Eric Barzdukas.
All right. Thanks, Dylan. So at this point, we have the ability to get audio video data from individual cameras, but as Dylan mentioned, that IO control layer was very interesting to us because that's how you could actually programmatically reach out to multiple cameras potentially. So we're going to walk through a couple case studies of what that full kind of exploit chain would look like. We've kind of worked to disclose with ThruTech. The case studies are all anonymized currently because we're still going through disclosure processes. But the first one here is one of the largest kind of home camera manufacturers in like North America. You can think pet camera, baby camera, things like that. And we'll step into that one. So the iterative process that we had for identifying IO control functionality that we were interested in, incorporating that into our SDK and hooking that into kind of local device vulnerabilities for compromise was to start with basically rooting the device, as Dylan mentioned. It's beating a dead horse to talk about IoT devices and like how bad they are, but it was basically, root the device, identify the interesting functionality. So you use your app, look at your dog photos or like look at your baby or whatever, capture that network traffic, analyze the network traffic, and then in conjunction with the firmware from the device, right? Like look through that code, do some reverse engineering, get some Ghidra time, a little bit of Frida, and then write a parser for it. So some of the IO control functionality is kind of what you'd expect from a platform like this. You can do things like enable or disable the LED that indicates when a camera is recording, right? So a lot of these cameras, you open up the app, immediately there's like a red LED, and that indicates that your baby's live on Twitch. The AV flow as well. It's kind of that movie scene. We could instruct cameras to like replay other footage to the mobile app. So, you want to break into the bank, you just replay the video of the vault that is a normal vault. There are a lot of IO control functionalities like get and set random device parameters. Less interesting implicitly, but that data wasn't sanitized. So there were like buffer overflows there. If you set the device name or Wi-Fi SSID, something like 44As. What really got interesting was the remote firmware update process on this device. The remote firmware update process basically the mobile application would reach out to your baby camera or pet camera. It would say, hey, there's an update at this URL. There was no check that URL was like vendor owned or controlled. So we spun up a DigitalOcean droplet. Firmware was also not signed or encrypted. So it's just a tar archive that you can send down. And then because this is an IoT device, the version of BusyBox was from 1982. And there was a tar symlink issue in BusyBox, which does not correctly handle symlinks. So you could overwrite arbitrary files because everything ran as root. And you could symlink. You could extract symlinks that you wrote on your local device for the archive. So we identified a couple important kind of like boot up scripts because of course there's like just boot.sh that handles everything after the device comes online. So in this instance, we were able to add just basically a netcat reverse shell. Kind of a fun aside, the sleep 12 was an arbitrary, like we just had to wait 12 seconds before things would work. 10 seconds, everything would crash. So putting those all together, we're able to start with basically a malicious firmware package on our own kind of DO instance. You then use that UID to like get the device credentials itself, so you can get that platform authentication to that device. Then instruct that device to pull down your kind of malicious firmware. It'll overwrite that boot.sh script, and then you get a reverse shell. You can do all sorts of things like make that LED strobe, whatever you want to do at that point. But that takes it from the ability to just view, sensitive pet pictures to actually starting to control devices through this platform, right? So here's a kind of quick demo. On the left side is, just Dylan being the attacker. On the right side here is a DigitalOcean droplet. Just proving that they're not on the same network. We have our tar archive with our kind of malicious firmware update staged on the DigitalOcean droplet. You'll see here we have set up a listener. We use the Python script to start that update process, tell the camera to reach out to our very real update. It'll then pull down that tar archive, and we sped this up because it's IoT. It had to reboot like twice and do a little dance. But once that update's pulled down, extracted, there's a reverse shell back to our C2, and everything runs as root, as I mentioned, so you're just in as root at that point. So this was a pretty straightforward example of this. There are a couple different ways that you can interact with this IO control layer. So I'll turn it over to Jake for kind of a more interesting custom interaction there.
All right. Thank you, Eric. Okay, so one of the things we noticed on some of the other models was not everyone was using the authentication the way that the Kali network thought you would. So probably 9 times out of 10, you would see username and password used. There were other methods, but we didn't see them used often. But one of the devices actually used hard-coded credentials here. And they used it, and they were trying to be clever. So what they did is they used the hard-coded creds, and they implemented their own challenge response authentication using the IO control layer. So you would use the default creds, and then you would issue a series of IO control messages to, in their minds, exchange a key securely and not actually show a username and password on the wire, which is a good idea. So for this one, kind of the same methodology we use that Eric described. We spent a lot of time looking at the mobile apps, using tools like Frida. Hopefully people are aware of Frida. Frida's very cool. Really helps us understand how these messages were being built. And then, of course, looking at the binaries, which for this one was MIPS. We saw, obviously, a lot of ARM and MIPS binaries through this. So looking at it on kind of both sides to understand what was possible here. So what did this authentication look like? Well, first, the smart camera would try to obtain a secret key. We're calling it K. And it's going to obtain that from its respective API servers. And this can happen at any time. This is usually when the device boots up. It'll connect to its servers and obtain this key. And it'll kind of store it in memory. The mobile app's going to do the same thing. So this was usually when you logged in the first time, but it could also be, it gets refreshed eventually. So both parties need this K variable. And then at some point later in time, the user would like to actually use their camera. So they'll launch the application. The app's going to use the Kali network to be able to locate the device. It's going to put those default credentials in, and then it's going to kind of initiate this IO control authentication process. So what's that look like? Well, first, the camera is going to create a encrypted blob by just taking some random data, encrypting it with the K value, and then sending that to the mobile app. mobile app, because it has the K value, will then decrypt the data and send that back to the smart camera. So you never exchange the key, but you are doing some crypto along the way. If the D value matches the original value, then the camera assumes that the authentication is passed, and then it will basically just start sending audio video data. So this looks pretty good to me. I'm not a crypto expert, but it seems like it could work. The only problem here is that it assumes that you can't impersonate a device, right? And the vulnerability that Dylan talked about permits exactly that, right? So the bug that we found will let you, attacker, maliciously register any device that you know the UID of, and we can use this to our advantage here to circumvent the way this authentication was built. We also saw some other pretty cool auth methods, just as an aside. I saw one manufacturer using like a public key model, which I thought was pretty cool, which is just a little bit better than the symmetric one, I thought. We also need a post-exploitation bug, right? So just getting around the authentication, that's cool. That gets you access to the audio video. But what we really want here is, like a shell like Eric described, or something a little more fun. Well, luckily for us, this IO control layer was pretty verbose, and this was a pattern we saw in a lot of these devices. The methodology Eric described was great. Buy a camera, get a shell on it, pull off the main binary, just grep for IoT, IOTC, I think was a string we used, and find this layer, and then just go through them and figure out what this thing can do. You'll find all kinds of things: reboot device, set network, change the angle of the camera, and our favorite, how about remote firmware updates? This one also supports that, and in kind of a similar way to the first device. So honestly, a lot of the stuff here, don't get hung up on the screenshot, just kind of showing the Python code of how you would format this. But the attack is essentially the same. You host a binary on some cloud server, and then you would kind of go through this authentication process and then serve this tar file to the device, which then gets unpacked, executed as root usually, and then you have your callback from there. Again, not signed, which is not great. They do have an MD5 hash for just the integrity of it, but that's not security. Okay, so we still have to break this authentication. So how do we do that? Well, the beginning is the same, right? The camera is still going to grab K at some point. We really can't influence that. The mobile app's also going to grab K, and we can't really change that. But here's where we come in. So we are the attacker. We're off on the side over here. Because the way the Kali network works, all you need to connect to a device, at least initially, is that UID. So again, we know the UID, and we also know the default credentials because they're just baked into the mobile app. So once we connect to it, it's going to then start that IO control process, and then it's going to basically challenge us with that C value. So it's going to encrypt some data, send it to us, and say, hey, if you really are who you say you are, decrypt this for me. And what we do is we just keep that connection alive for a little bit. Then, using another thread, we will exploit the vulnerability that Dylan described. Think about that earlier video. And what this is going to do is it's going to poison the network, right? So now any subsequent connections to this camera are going to go to us, not the real camera. And it's important because we still have a connection to the real camera here. So we kind of keep this one alive so that we can still get to it, but anyone else is not going to be able to. And we just wait. And then eventually some user wants to see pictures of their dog or whatever. They will open up the app. It's going to reach out to the Kali network. Kali network says, yeah, if you want to connect to that, go to this attacker over here. And because of the process, is going to request the C from us, which, of course, we have C. We don't have the key, but we have the C value, which we'll just pass that along. And then the client will decrypt it for us, right? And then it'll send it back to us, which we then send to the smart camera as if we were a valid user. Camera says, oh yeah, you do have the key. Let's share audio video. And then we go ahead and trigger that remote firmware update. So got a fun little video for you here. Bottom right is just the Apache access logs. Top right is going to be a little callback. So very similar to the earlier screenshot. And then you have these two boxes on the left over here. The top one is going to be that kind of keep alive message. So just keeping the connection alive, waiting for the challenge to be presented to it. The bottom left here is going to be us poisoning the network. So you can assume like at that moment right there, a victim opened up the app, and then it's going to pass it to the top left, and then you can see the get request for the tar file, and then the callback, the top right, and here we are as root again, because of course everything has to run as root. So that's fun, right? But one thing that we've kind of been glossing over, and Dylan's going to talk a little bit more about, is the importance of the UIDs, because everything we've talked about hinges on the ability for an attacker to have UIDs. So when we were presenting this to other people, we got that question a lot, like, oh, how do you get these UIDs? So Dylan's going to talk a little bit about that.
Yeah, thanks, Jake. Yeah, I'm sure you've been wondering, how do you get a hold of these UIDs and make your own botnet here? The UIDs were actually infeasible to brute force. They were 20 bytes of pseudo-randomly generated data. But, we weren't really going to stop there, because we realized that protecting these UIDs with this vulnerability out there becomes of the utmost importance, right? So we found that often these IoT camera apps would write their own APIs that would access the ThruTech UIDs. They would then be passed to the IoT camera and then would be used by the SDK to connect to the Calais platform. So you can picture something like a get API device, get UID API endpoint. So we wanted to assess kind of in our case studies that we looked at, were these APIs implemented correctly? And could someone actually grab a large number of UIDs and exploit this on a mass scale? What we found was these APIs were not implemented with security in mind. Most of them returned the ThruTech UID through an API tied to some account, right? And for some vendors, these API calls were unauthenticated entirely. Sometimes they used default baked credentials. And in one case, actually, we were able to just burn through and enumerate like a ton of UIDs that we could then, if we wanted to, use our device impersonation vulnerability against. And we also looked at just the API infrastructure and found that it was also built without any inkling of security in mind. So did some surface level reconnaissance, sent a malformed basic auth header, and received a Django debug mode environment variable dump. We didn't move further here to keep things legal, but you can imagine that with APIs as insecure as the ones we looked at, a mass compromise of these ThruTech UIDs would certainly be possible. And now I'm going to pass things along to Eric once again, who's going to talk about some key takeaways.
Thanks, Dylan. So kind of a couple key takeaways here, connecting back to like the title of the talk. IoT, still a hard problem. Hard to fix in the field, but more importantly is going to be like, who do these devices actually trust as vendors, right? Who's providing the complex functionality, right? A lot of devices are, purchased from a third party that actually makes the thing different, sweatshop, puts all the code on it, marketing team like resells it in, kind of the richer countries. And there's a whole like messy chain there to step through. The other item kind of as a takeaway is, again, specifically to the Calais platform, if you're managing devices, if you're integrating into vendors, make sure you're keeping things up to date. You're kind of having those hard conversations with your vendors about, how is the data actually protected, or like, how does this stuff actually work, right? A little bit of kind of time up front on understanding that would save, a couple of nerds like us emailing you and, talking about the dog photos we were able to get. And then the other kind of last item is just protecting data that other vendors might expose that your camera's integrating with, right? Like a lot of the threat model for, I think, camera companies is specifically that audio video data, but like the account information that's actually used on the vendor kind of platform itself, right? You got to make sure you don't dump Django environment variables when your web app doesn't handle input, things like that. Other than that, thanks to kind of CISA, ThruTech, kind of the various vendors that we're working with, and of course Nullcon. So that's everything we have. Happy to take questions if there are any. Thanks. Yep.
So that was pretty cool. I really like this.
Thank you.
As you said earlier, like all of this on like the UID. Have you done more research in how these UIDs are being generated? Because I'm thinking it would be pretty cool to have like as many babies as possible on fish.
Yeah. Yeah.
I want to have a specific baby on fish. I cannot get there. So I'm thinking, like, have you looked into, for example, identifying certain UID patterns connected to certain vendors, to certain production batches, or something like this? All right.
Yeah, also a fan of finding that sweet baby footage. So there were some fixed patterns within that ThruTech ID. For the actual generation, do you guys have more to add on kind of how that was generated?
Not something we really had access to.
Yeah.
Definitely we're interested.
Which is really understandable. I'm just really just wondering if you have the chance to actually get insight into how these are generated and if there's any connection with the manufacturing date, vendor, and so on, because that might kind of move it away from, hey, we can build a botnet to, hey, we can look at Trump's baby. Yeah.
Right. Yeah. And the question, just to repeat it, was, did we notice any patterns in the way the UIDs were generated? Really, I mean, there are some patterns in it, but it didn't seem to be device specific or even like vendor specific, unfortunately, which I mean is good, right? I mean, you'd want that to be the case, I think. I think we were really happy to see that there was pretty high entropy between them, even between like if we bought 3 cameras from the same manufacturer, they could be like completely different, right? So there wasn't like four bytes that were like that company, then 4 more for like a region or something. So it did appear to be pretty random for at least I think the first 16 bytes were pretty random.
Yeah. Yeah, that's a good question. That's something I was definitely interested in. I did some probabilistic analysis on it. Given sort of the number of bytes we were dealing with, we really, even if we had a huge farm of servers, I'm talking like 100,000, it would still take us like hundreds of years to crack the first one with 50% probability. So definitely not within the realm of possibility to brute these. That was definitely something we looked at though. That's kind of why we moved to looking at API security, because that is going to be, as an attacker, your way to get those UIDs. Yeah.
The one other item, there are like troubleshooting threads online where people were like posting that information. So not a scalable attack, but if you want to find them, they're out there on, Reddit. So no, sure. Then
There are still a lot of questions about UID.
Sure. Yeah. No, yeah. So when was this kind of conducted off or on the clock, things like that? This was entirely off the clock, just buy a keg, hope people stay in the office and want to like chew on some cameras.
Unless the guys start paying for the tickets. I mean, the problem is that there's not many companies around the globe who are supporting the offensive research, especially outside of the area. Yeah, you have like working bands, you can do a competitive intelligence in tech bands. And that's why I'm like curious. Yeah, I don't see this command just very often.
Yeah. Yeah, no, definitely. They were a huge help going. Sorry. Yeah, I mean, essentially, once we got through to the kind of the minimum viable stage, there was a lot of help for disclosure. But yeah, it was, we're just chewing on cameras.
Yeah. And one thing also to keep in mind, we bought like 12 or so different models. Not all of them were using ThruTech. There was, I think, a couple other platforms that we really haven't looked into. Some of them have research already out there, so they were less exciting. But it's not like every one we bought was ThruTech. It was, those ones seemed more exciting because when we started looking it up, there really wasn't any technical analysis. So it was kind of like a new technical exercise for us to go through. But there's definitely other protocols that are used that, like, we didn't just pick ThruTech. We're like, these guys are going down. It just happened to be like one that was popular and, the process we went through. Yep. Oh, sorry, maybe first. Yeah. The question is, what if you're on the same network as the camera and it's completely broken? It just broadcasts. It says like, hey, if you. So we didn't talk about that, but if you are on the same network, before it reaches out to the servers to try to find it, it's going to say, is anyone on this network this ID? And you could just respond, and it would give you the creds. So. Yeah. Yeah, it's going to be your friend's baby, right? So luckily, hopefully know that person, but yeah. they care, and I think at least the companies that we've been working with have been pretty receptive, like letting us talk about it and kind of share the information. They are very hesitant to be named, and that's why we tried pretty hard to make sure it's not like mapping back to an organization. But I think just the nature of it, right? The fact that it's camera footage and camera audio, there's some concern around it. I do think through tech, I mean, they work with us. They've shared their recommendations on things. I think my recommendations would be a little bit different, but they did share kind of the way they would mitigate this and encourage their vendors to update. So, but I think the response is good. Yeah, we can help them with that if they'd like. Yeah. Yeah, the question is how cheap were some of these? Yeah, I mean, I would say cheapest probably $20 or $30, but maybe you know the top.
Yeah, at the higher end, we had like a kind of small business home security system that I think was like a $500 $600 initial buy-in, and that's like your local mechanic or your local kind of retail store. It comes with a couple cameras, like a box to manage everything. So at that level. Are they more receptive? And I think we're still working through kind of the process there. So don't have a great answer. I don't know that monetary value of camera was like linearly linked with how much people cared, but I think there were the kind of the low technicality of like the end user for a lot of cameras, right? Like, you know, people who just want to have the ability to watch an animal at home, not going to be sophisticated users, and they're going to care a lot about like that brand image. So the companies that relied kind of directly on people at that level buying it seem to be a little bit more, I think, ready to roll up sleeves.
Yeah, the question is, do the recommendations work? And the answer is yeah. I would say I'm okay with it. We didn't talk too much about what the off-key feature is, but I'll go back to that slide. Unplug it. It's not really like their recommendations were bad. I think it's a tough problem to solve when you're basically saying, you know, you have these millions of cameras and like the platform is or was broken. So what if you like updated it all to use this new like feature set? And so, I mean, the real answer probably is the old version should just be decommed and like it doesn't work anymore. And then those aren't features. Those are they're needed, but using them will require like the vendor to do something, right? So if you're camera manufacturer S, you are going to have to make the change and support these new functions. And like the DTLS feature, I mean, it's an SSL thing, so you might not even have a chip that's fast enough for this. Most of them are. I mean, they're cameras, so they usually do. But that was one of their pushbacks, was like not all cameras can support the suite of SSL, so that feature like might not be something you can turn on. And I mean, I get it, but you still want the data to be like encrypted and safe. So if you use those features, a lot like this stuff does drop away. So I'm happy about that. I just think the old like, if it's not fixed, like all the cameras we didn't buy, right? Like what are they doing? I'm not sure. Yeah. Depending on the features that are used, the question is the video encrypted? The video can be encrypted, but depending on the different features used, it might not be. Question. Yeah. Sorry? Yeah, I actually did see a couple of them that were using it. The question is the DTLS feature used? I had to like really look up how it's implemented technically. It's a kind of I don't know if it's an obscure feature of SSL, but it's definitely not a very common one. They were using a DTLS PSK. So there's like a PSK exchange as part of it, which derives some other keys, and then it's essentially a SSL wrapped UDP connection to pass the data, which is actually really cool. I just wish that was on all the time because that would more properly protect the data in transit. Any other questions? Okay, cool. Well, we'll be hanging around here. Thanks all for joining us, and hope you guys enjoyed the content. And yeah, thanks to Nullcon for having us out here.